Good afternoon, ladies and gentlemen. How is everyone doing?
I'm feeling great, and I hope that everyone's doing well either and radiates the same energy so we can start our second plenary sessions.
By the way, I noticed something different about the way some of our guests are dressing.
And not only our guests, but so do us as well. So actually, we're currently celebrating the National Batik Day, and in order to preserve one of our cultural legacy, we specially dress in batik.
Indeed, we hope that we can share our energy to hype up your day with our batik. So, without further ado, welcome back to the plenary session of the Suhadi Reksawardoyo International Seminar on Chemical Process Engineer.
STKSR 2025. Good afternoon, ladies and gentlemen. It is an honor to welcome you back as we commence our second plenary sessions, a continuation of yesterday's program, where we will further explore the key insights and perspectives from our distinguished speakers.
Before we start our session, let us introduce ourselves. I'm Francesco, and joining me, Leonie, as we will be guiding today's session.
Before we proceed with today's agenda, we would like to take a moment to acknowledge and sincerely thank our sponsors whose generous support has made this event possible. Our heartfelt gratitude goes to PT Pertamina Persero,
Soltec,
PT Zeus Kimia Tama Indonesia, also known as Zekindo,
and also PT Bukit Asam.
We deeply appreciate their contributions and commitment to the success of this program.
Once again, we would like to extend our gratitude to all our sponsors for their valuable support.
Now, we will proceed to our next sessions, which will focus on the theme of sustainable energy storage. As you may recall, in yesterday's sessions, we explored the prospects of battery development and Indonesia's energy policies. Today's sessions will further highlight the innovative approaches and insights to sustainable storage solutions.
Correct. And this session will be led by our moderator, Mr. Hari Devianto, a lecturer of Chemical Engineering from Institut Teknologi Bandung. To Mr. Hari Devianto, please join us to lead the second plenary session.
Okay, thank you very much. So I don't need to introduce myself, right? You can see directly here. Okay, before the session start, allow me to invite both of our distinguished speaker. Please welcome to the stage. The first one is Professor Nurak Danurak. Okay, as you can see here, he got his PhD from Colorado School of Mines, United States, and doing a lot of postdoc, formerly in Japan and also in Australia. His work currently as a professor in chemical engineering in Thammasat University, Thailand. Let's give again a big applause for Professor Nurak Danurak. Okay, please have a seat. The second one, allow me to again invite our famous speaker, Dr. Kaijian Zhu. Let's give him a big applause. He got his PhD in Faculty of Science and Technology, University of Twente. He got also postdoc in Twente as well as Hong Kong. Currently work as a researcher focusing on optimizing nickel oxide to achieve highly efficient dye-sensitized photocatalytic using solar water splitting and CO2 reduction. Again, let's give a big applause for Dr. Kaijian Zhu. Please. Okay, before we start, allow me to give you a brief summary. So you will have more or less around 25 minutes, and you may see later on the timer over there in the center. They will give you a signal, and if you still, once you finish, the second speaker will also give the talk, and totally maybe around 25 to 30 minutes for question and answer. Okay, now let's give a big applause first for our first speaker, Professor, yes, no, that's true. Professor Nurak Gisdanurak, please. The presentation.
Okay, distinguished professors and research fellow in this hall, good afternoon. Today, before I begin the talk, I would like to express my sincere gratitude to the organizing committee inviting me to this talk, and also thanks to the hospitality and a warm welcome and also good arrangement of the ITB members, both professors and students. Thank you. Well, today I am excited to share with you on EV. Next, please. Okay, let me try using this. Let me try using it. Okay. We're excited to share with you about the EV battery work. And I am Nurak Gisdanurak, and professor in Chemical Engineering Department, Faculty of Engineering in Thammasat University. Somebody may not know where we are. So if you look at the map on the right-hand side, the university is about 50 kilometers from downtown Bangkok, and it's about 20 kilometers from the second airport, which is very convenient because you can, that is a direct flight from that airport to Jakarta, which make me very convenient to come here. What should I do next? Okay, this one, right? Yeah. Okay. Like yesterday, we talked about in Indonesia. There's a lot of, so many natural resources in Indonesia in terms of precious metal, particular to nickel, right? But what we are doing here is just about the reason that I do about the recycle thing, because two reasons. One is that, as you can see that, cannot use that. We got industrial waste import illegally from other country, and all of them are electronic waste and electrical battery, which has been spent. And what they do, they come for the sorting business and separating things, and they got the black mass back to their country, the valuable metals back to their country, which is left the chemical waste behind in our country. So the government think that why don't we try to do ourselves in terms of that. Secondly, we have a very small scale, very small plant, or only one small plant to work with the EV battery. However, this controlled battery is only for the big car company. So after the high treatment of temperature by incineration process, the product of black mass also going back to other country else for the extract, for the metal, precious metal. So these two reasons is to make the government or the policy to think about why don't we start to think about the recycle thing in our country. The one that I work will not focus on the control EV battery because those has been very dangerous for the student to work with. So we are working on only the electronic appliance battery. Electronic appliance battery that I will focus are about daily life use the battery like a rechargeable battery and also some motorbike battery, as you can see here, and also some of the drone battery for the drone agricultural work, as you can see on the right-hand side of the slide. In that battery, of course, people understand that there are some precious metal composed in the battery. For example, lithium, manganese, cobalt, copper, and nickel, right? And it's quite high. However, we don't have this kind of natural resources in Thailand. So what we have to rely on, if some EV plant need to be set up in our country, it will depend on the import price. As you see on the right-hand side, the price of copper, nickel, and lithium is quite high. So the price of EV, the electric car, or even the motorbike will be getting high as well. Of course, when you want to get the precious metal, we need mining activity. We need mining, industrial, right? I agree with that. However, the more mining we have, the more environmental in surround area, the area will be jeopardized very fast. And as you can see from the picture on the top, this is related to Indonesia, of course, in some area. And there has report that a lot of high concentration of heavy metal has been released to the water for their consumption water. So this is not very good. One of it, you will see this mining activity and environment. It seems to be people working in this mining get abused by those kind of pollution. From the right-hand side, that's what they produce, graphite. And some on the left-hand side, this is the picture in Africa, the country in Congo, and they don't have very much of concentration of the precious metal. So what they do is to just grinding by hand and then putting in the small incinerator on the right-hand side at the bottom side. So people have been abused, and the health risk will be give them a lot of toxics, health toxics. Over than that, if you look at the price on EXW price, the price I have converted from dollar to Indonesia rupee is not very expensive. So this must be one thing that we have to concern. So what we need to do is, why don't we go for the circular economy, do something of the recycle. So Thai TU or Thammasat University collaborate with EGAT, Electricity Generation Authority of Thailand. We work together for like 6 years, and then we start to work in 3 projects consecutively. Starting with the laboratory scale, we use a very small battery from Tesla, and then we set a small scale as in terms of crushing on the left-hand side, the middle picture, and then we use the black mass after screening on how can I make the pointer? No. I don't know. Okay. After we did the crushing, we do the screening, and then we use the black mass for precipitation work on the one below. So in this laboratory scale, what we learn We understand how the battery fabricate. We understand how we can extract those precious metal out. So the condition that we get from this laboratory scale, we will move to the right-hand side. So it means that there are two processes put together. One is first part of lithium battery recycling process. The commitment on that is to get the production by 400 kilogram per day. And then after that, the black mass will go to the second part of the process. That will be under hydromet process. And we expect to get around 400 grams of lithium per batch. Looking at the crushing process, we completely set up the process of crushing process imitate from the laboratory scale, and then the operation has been launched in December 2023 by Director of University and Governor of the EGAT come together and open the process. The product, we got the product on the right-hand side. The product, as you can see there can be classified in very fine particle and some rough particle. In more detail, the process is composed by one grinder and one crusher. Along with a screener, we have 3 sets of screener for different size, and also we have 3 sets of cyclone, 3 sets of dust collection, which including cyclone and backhouse filters. There are about 14 points for sample taking. 14 points. We correct all the sample from 14 points, and then we characterize by XRD, XRF, and ICP-OES. On the right-hand side, those are our products in the different batch. Because the different batch, it means you need to control the income of the raw material. Different kinds of battery, different property or characteristic of the black mass you will get. Okay. Based on chemical engineering basis, what we have to do is you have to talk about basically in terms of mass balance, right? So we start with the functional unit of 26 kilogram of battery from the motorbike, and then we separate everything out we did disassemble the battery and then take everything out. As you can see, we can get different kinds of waste, However, if you look at this, if you convert into 1 kilogram of the EV battery, spent EV battery, we can get the blue lines, which are about 70% of the black mass that we can use for the further process. Along on the bottom side are the waste that we can work on the disposal properly. For example, aluminum we get about 10 kilogram of aluminum. We can do some incineration and ingot of that. We did some life cycle assessment comparing to the black mass production from the incinerator that has been existed in our in another province by using the CIMA Pro 9.4 and then compare between crushing process and mechanical process and incineration process. It's very clear that all 5 categories of the environmental impacts, all 5 categories produce very small amount of impact comparing to the one with incineration. So this is quite good to convince what we should have the real factory in Thailand or not. A part of the construction, we also working with the education. We work on the education to the student, to the hospital, and then talking about how can we work with the EV safely. And also we have done some public hearing. So people in that area or that the factory located can be understand how they can understand about the process and also the impact that they will get. We have done also something with the electrostatic plasma. However, this one doesn't work very well in terms of separation of black mass particle. Okay, now I finished the first part of crushing. I'm going to the below box, which is about the second part. And this second part will follow the hydrometallurgy process. The left hand side is the black mass we got from the first part, and the right hand side are all activity that we start working on very small scale of 20 liter of reactor capacity. Well, sorry that our student didn't put the laboratories suit properly like your student here. And what we have done is to work on the leaching and also filter of the product out. The product will be was analyzed by XRD, XRF, and ICP as well. And also this all the picture we get. The product on top after filtration, we get 100% of graphite. We have the very good fingerprint of graphite in the top, and also the green product, which is composed by nickel and copper, can be sold because of the composition of nickel here, more than 45%. The product in Indonesia, they sell, put in the market of purity of 45%, I think. So this is about the compound that we can do something in commercial. We also get the manganese carbonate and also lithium on the right hand side. And all XRD spectrum show very good fit. So this is our material balance. From 2 kilograms of black mass, what you can get is graphite, copper nickel compound, and lithium carbonate in the final part. And the electricity that we spend for each run is about only 2 to 3 electricity unit. So it's not much energy consumption. And water that we use in this process is around half cubic meter, which of course will contribute to wastewater for 0.5 cubic meter as well. We also calculate based on how profit, but based on the profit margin. And as you can see, the lithium waste is about the black mass can be, after production, will cost about 100. After using this reactor, it's a bit difficult to control as the small scale, like 20 liter reactor capacity. So the product will be different, the color will be different a little bit. However, based on the characterization, we gave very much the same thing. And under 10 kilograms of black mass input, we can produce around copper nickel compound. And the purity of the lithium carbonate that we get is less than 20 milligram of kilogram, 20 milligram of kilogram of cobalt, nickel, and copper. Sorry for the mistake, typo. And this is our sequence product. starting from black bass up to the lithium. We are working with, look at the utility we use based on 10 kilogram of black mass used, only electricity of 27 kilowatt hour or unit has been used, and wastewater contribute about 2.4 cubic meter. We also start to have some visitor, and if you look at, that is all about my research. However, I would like to you to take a look on the battery life cycle system. Based on the recycling process that we have. Before that, you need the correction unit, you need the sorting, because you need the same raw material input, and also do the discharging unit before going to the recycling, right? After that, all the compound after purification will go to fabricate again. So based on this, we can have more research into it, like we send those kind of metal to lithium, we stucking on the research because we have to find enough lithium battery waste. So we need correcting nodes, which Dr. Atitya said yesterday morning. And also we need a sorting machine to make sure that we have only NMC going to the process or LFP going to the process. We need a very automatic discharge unit, and also taking care of the process of crushing and purification of metal, and some regulation need to be put in the Department of Industrial. Right now, we have ongoing research. Yeah, for example, CO2 utilization for the lithium recovery and utilization of purification of nickel copper. We are working with several universities, for example, one from Taiwan and one from France. So I'm very welcome some students would like to join, or some collaboration from Indonesia. This is my last slide. And of course, I would like to put one phase of this. It is, we should use less for the longer. Thank you very much.
Okay, thank you very much. Again, big applause for Professor Nurat. Yes, have a seat. Now, let's move on to the second speaker. Please, Dr. Kaizen Zhu, to deliver your talk. Yes, the time is yours.
Good afternoon, everyone. My name is Kaijian Zhu from Sydney University of Hong Kong, and it's my great pleasure to be here to talk. Since we know that hydrogen is a very important building block chemicals for a lot of different applications, and our world is facing the energy transition. Therefore, the hydrogen demand is expected to grow, to increase significantly in the following years. However, unfortunately, only a very small portion of this hydrogen was produced from the renewable energy source, so green hydrogen. Most of them are still produced from the fossil fuels like steam methane reforming, so-called gray hydrogen. Therefore, it is very important to find some techniques which can directly convert or produce some green hydrogens from the renewable energy source. One of the promising technique is called photovoltaic plus the electrolyzer. So in this system, it's quite mature technology already, and some company already have a relatively large scale factories. But if you see from the structure, it has three components. One is the photovoltaic part, solar cell, and we need to have a DC-DC converter to convert the electricity to drive the water electrolysis. Therefore, these three components will add up to the balance of system cost. Therefore, according to the analysis, the levelized cost of the hydrogen produced by this method is around 4 to 10 US dollar per kilogram, which is a bit higher compared to the conventional hydrogen production method, so SMR. So another technique we are working on is called photoelectrochemical process, which can integrate the solar LED capture and direct convert it into hydrogen in one cell. Then in this case, because of this integration, it is, in principle, can reduce the both cost. However, because this cell does not undergo an industrial optimization yet, therefore this cost of device add up a lot to the LCOH values. But in the future, as expected, if this device cost decreases, then the LCOH value can be comparable with the PVEC or even lower. Additionally, if we incorporate a light concentrator into the system, then it is expected to have even lower LCOH values, which might be possible to lower than the SMR method. Therefore, nowadays, our target or our aim is to reduce the PEC module cost. So we need to find cheap materials used for the solar hydrogen production. There's a lot of different electrodes used in the photoelectrochemical cells. Here I just want to introduce one of it. It's called dye-sensitized photoelectrode. So basically it has very simple structure. We have a metal oxide film, which is basically nickel oxide for the cathode and titanium dioxide for the anode. Then we will have a dye and a catalyst on top. The metal oxide part, it can be simply use the spin coating or the screen printing, which is easy to be scaling up. And for the dye and catalyst loading, we can just simply dip the electrode into the solution containing the dye and catalyst, and we will get a very nicely sensitized electrode. And also, usually the dye we use only contain the element like carbon, oxygen, sulfur, nitrogen, this kind of earth-abundant element. Therefore, there's no source kind of issues in the future. Also, the optical property of this kind of dye can be very precisely controlled. Use this dye as an example. If you only control the bridge between this donor and the acceptor group, then you can tune the light absorption coefficient. And also, if we tune the functional groups, then we can precisely tune the absorption wavelengths of the dye. And furthermore, we can co-absorb different dye together on the same electrode in order to fully use the solar spectrum. And another important feature was mentioned is this dye-sensitized electrode can respond to the light with very low intensity, such as the indoor light. Therefore, it is perfect for the indoor light applications. And of course, this kind of electrode has some problems. The main problem is that the efficiency of this kind of electrode is very, very low. This is mainly because of the fast charge recombination between this nickel oxide and the dye. Therefore, my previous work was focused on this dye and the nickel oxide interface in order to understand what causes such a fast charge recombination between this dye and the nickel oxide and try to improve the performance. So I started from working with this P1 dye, which is a commercial dye as a benchmark to sensitize our nickel oxide. And since the nickel oxide has been reported has a poor hole mobility, therefore we doped the nickel oxide with copper to enhance the conductivity of this material. And we see after doping there's no obvious difference from the morphology and the thickness. But when we check the photocurrent in the PEC cell, we indeed see the enhancement. However, when we check the performance, use it as a solar cell, dye-sensitized solar cell, which is in the acetonitrile-based condition, we found this short circuit current decreases, so which means also the light conversion efficiency decreases. So we are very much interested why this same materials shows quite different behavior in different environment. Therefore, we designed a very simple experiment to study the effect of this environment. So basically, we put a piece of sample into a cuvette, then we fill the cuvette with different environment. For example, acetonitrile to mimic the working condition of the solar cell, and the phosphate buffer solution to mimic the PEC condition. And also we measured it with only filled air with different humidity. Then we used a technique so-called pump probe, which is also called transient absorption techniques. So the basic principle is like this figure. We have a laser pulse which split into two, and the one with the high intensity was used as a pump to excite our sample. Then another weak pulse will go through a delay stage, then as a probe to probe the excited absorption of this light. Then we can tune the delay stage to change the delayed time. And this is the setup that I used for this experiment. Then the result turned out the same sample shows very significant difference in different environments. So it turned out that in the phosphate buffer solution, which means you have a lot of water, then you will have a very fast Hall injection from the dye to the nickel oxide. But in the meantime, it also has a very fast charge recombination between this dye and the nickel oxide. And then later on, because there's a lot of factors may affect this process, but later on we see it also shows this similar behavior in the air with different humidity, which means this is because of the water. More specifically, it is because of the surface hydroxylation of the nickel oxide. So we then draw this diagram to explain the phenomena we observed. So basically in the phosphate buffer solution, because we are surrounded with water, therefore it has a lot of hydroxylations on the nickel oxide surface, which attract fast Hall injection from the dye to the nickel oxide. As the nickel oxide has a poor Hall mobility, therefore the injected holes are mainly pinging at the surface. Then in this case, it will attract the electron back to have a fast charge recombination. And later on, we found this surface hydroxylation has much more impact compared to the bending cost of the external potentials. So since nickel oxide has been studied for many years, but the performance is still very low, and also is sensitive to the water, therefore we are thinking, is there any alternative materials can be used to replace this nickel oxide? Then one material came into our mind is this carbon oxide, because it has a higher band gap, which then can make a transparent electrode. Then it also has a deeper valence band position compared to the nickel oxide, that can provide a much higher voltage. And also it has a high theoretical Hall mobilities, which is good for the charge separation. But in the literature, it has some synthetic challenges, because it is very difficult to get a pure phase of this material, and also the particle size is usually very large, which is then not good for the dye sensitization. By modifying the method from the literature, we can get a nicely carbon oxide film apparent from this XRD result. And by checking the multi-shot key, we confirmed this material is a P-type semiconductor, and it indeed has a deeper valence band position. Then also the particle size is around 10 to 20 nanometers, which is perfect for dye sensitization. But the problem is that we found the thickness is only less than 50 nanometer, which is then not good for the dye sensitization, because after we loading the dye, the light absorption efficiency is only 10%. Separate the electron and the holes, then in this case we can enhance the photocurrent. And in the dye sensitized electrode, except with metal oxide, the dye is also an important part. And we noticed this dye used in this application usually is a donor-accept dye. So it has a donor group and an acceptor group. Then this kind of donor-accept dye will, after it got excited, it will undergo a twisting, so-called twisted intramolecular charge transfer. And according to our calculation, our P1 dye will also undergo a very large degree twisting after excitation. And this twisting leads to the excited state energy decrease around the 0.36 electron volt. Therefore, this twisting is kind of energy loss. Therefore, we think, is that possible to inhibit this twisting in order to save some energy for the later reactions? So our strategy is to co-adsorb this myristic acid together with P1, because this myristic acid has a long hydrocarbon chains which can provide a local apolar environment to limit the twisting of this P1. And we confirm this the limited twisting by using the photoluminescence spectra. As we can see from here, it has a higher PL intensity, and also we blue shifted the spectra, which is indicate of the blocking of non-radiative decay channel, and we shift the PL emit from the TST state to the LE state. Then we found, even though with co-adsorption of myristic acid, we will have less light dye loading, which means we will have a less light absorption, but we see the enhancement of the photocurrent. More interestingly, we found with the presence of myristic acid, we see bubble generated both on the counter and the working electrode without additional of proton reduction catalyst. This is very interesting because we did not see it on the nickel oxide P1 itself, because P1 itself do not have the ability to split the water into hydrogen. Then we use the home assembled in situ photoelectrochemical model. Do not fully understand the reaction mechanism yet, but we think the saved energy, excited state energy plays a very important role in it. Then as hydrogen evolution is only half part of the PEC water splitting cell, another half part is usually oxygen evolution. Then this oxygen evolution has a high theoretical potential, and also because it involves 4 electron transfer process, therefore it has a high kinetic overpotential. Also the reaction kinetics is very slow. Also oxygen as a product has relatively low economic values. Therefore we are thinking, is there any other strategy can be used to lower the LCOH value? Oh, wait. But does not work? Oh yeah, okay. Okay. So then we found using this cell, we can do way more reactions than water splitting. We just need to, for example, change the feedstock into this device, then we can do different reactions. Therefore, our strategy is to see if there's any alternative oxidation reactions which can generate value-added chemicals. Then in this case, we can increase the system competitiveness. So the first example I want to say is instead of split water, instead of water oxidation to oxygen evolution, we can direct the reaction to the hydrogen peroxide production. Because hydrogen peroxide has a relatively higher market value compared to the oxygen, and even though it has a higher theoretical potential required for the hydrogen peroxide production, but because it only involves 2 electrons, therefore it offers the kinetic advantages. And according to the technical economic analysis, it turned out that when the hydrogen peroxide price at around $0.85 per kilogram, then we only require solar to hydrogen efficiency around 10%, and with 100% particle efficiency to hydrogen peroxide, then we can already achieve the LCOH same as the SMR method. Therefore, it is the strategy here is to tune for the 2 electron water oxidation to hydrogen peroxide instead of OER. Then we start with a very famous photoanode materials bismuth vanadate. It was very commonly used in the water splitting and also the hydrogen peroxide production. And we found this material can be instantly transformed to the bismuth phosphate in the acidic phosphate buffer solution. Then we systematically studied this transformation. Then we found the pH light potential has a huge impact on this process. Then we found with higher transformation time, which means higher surface bismuth phosphate, we will have a higher particle efficiency towards to the hydrogen peroxide. But because bismuth phosphate is a large band gap material, more bismuth phosphate means we have less light absorption. Therefore, there is optimal transformation time. And also, we studied the effect of the OH and the bicarbonate ions in the electrolyte. we found this bicarbonate has much more significant effect on tuning the selectivity towards to the hydrogen peroxide. Therefore, it is important to say that instead of calculate in the future catalyst design, instead of calculate the absorption energy of the hydroxide groups, it is more important to calculate the absorption energy of the bicarbonate. And another example I want to say is the PET upcycling, because PET bottles or PET box is very commonly seen in our real world, and they are not properly treated. Most of them are just disposed, not properly recycled. But if you see from this figure, you can see after proper treatment, it can depolymerize it into some monomers, and from different treatments, they all gives the monomer of ethylene glucose. And this ethylene glucose can be further oxidized into different chemicals. And now there's already a lot of research study this ethylene glucose oxidation, but most of them, especially using the photoelectrochemical method, they always get higher efficiency to the formic acid production. But if you compare the market price, we will see the formic acid has a very small difference compared to the ethylene glucose. But instead, if we see at glucolic acid, it's a much higher market values, which means it's much more valuable, and we should target it for. So in this case, I used the titanium-doped hematite as my photoanode, then to do this EG oxidation reaction. And we found with the presence of this ethylene glucose, we indeed see a higher photocurrent. This is because EG oxidation is thermodynamically more favorable. And then when we look at the product, so from our device, the main product is formic acid and the glucolic acid. But when we enhance the potential, which means we enhance the photocurrent, we will see an obvious decrease on the glucolic acid production or accumulation. This is because we found the glucolic acid is much more easier to be oxidized on the hematite. Therefore, it is difficult to accumulate the glucolic acid in this system. But recently, we found that there is a catalyst which can work perfectly to convert the ethylene glucose to glucolic acid in the dark and the room temperature and the ambient pressure. But I can't say what catalyst it is yet because we are submitting a patent for this. And we found the factors like temperature, oxygen, and sodium hydroxide concentration affect the production rate a lot. And then if we go back to the photoelectrochemical cell I just discussed, so we see that oxygen can be produced with around 50% on the hematite, and also the heat we can get directly from the sunlight. Then also sodium hydroxide was used as electrolyte. Therefore, we have a concept that we can incorporate this catalyst into this PEC cell. Then in this case, it can use the oxygen generated on the anode, then use the heat from the sunlight, then to facilitate the EG conversion to the ethylene glucose. Then indeed, we see that with the presence of this catalyst, we see a huge enhancement of the glucolic acid production rate. And with higher potential, or potential with a light concentrator, which means we have a higher photocurrent, we have more oxygen produced, then we will have an even higher glucolic acid production rate. And of course, the selectivity is also enhanced in this case with the presence of catalyst. Then finally, we also made a demonstration using the real-world plastic bottles. We first use a plastic bottle, then we hydrolysis it. Then after reaction, we acidify the electrolyte, then we can easily separate this taric acid from this electrolyte. Then we also, in the electrolyte, then we detect the formic acid and the glucolic acid. But we found the glucolic acid production became slower with the time goes. This is because of the presence of this TPA will poison our catalyst. But this catalyst can be easily refreshed by just wash the catalyst again, then the activity will goes back. Then we also did the techno-economic analysis on our setup on this device. We found if we target for the formic acid, even with 100% particle efficiency, and high current, we still cannot get positive net present value, which means it is non-profitable. But if we target for the gluconic acid, only 30% of the phytic efficiency, we can already generate some values. And with our coupled strategy, we can boost this MPV up to 10 times. And these are just two examples. There's way more important reactions can be targeted. And we already wrote a review paper on the different reactions, and we categorized the reaction product according to the market price and the market values, market price and market demand. So to conclude, we think this dye-sensitized photoelectrode is promising for scaling up, but it is now limited by the low performance. And as a nickel oxide, as a metal oxide, we should consider about the surface hydroxylations when used for different applications. And carbon oxide is a potential alternative, but it is now limited by the thin film thickness. And for the dye, the twisting should be considered for the design. Maybe we can design a rigid dye by introducing some static hindrance in order to prevent it from twisting. And coupling hydrogen production with value-added oxidation reaction is economically favorable, especially for example, the hydrogen production or PET upcycling. And of course, there's more reactions need to be targeted. And yeah, finally, I'd like to thank my collaborators and also the foundings. Thank you.
Okay, thank you very much, Dr. Kaizen Zhu. Let's give him a big applause. So now we enter the Q&A session. We will have more or less around 30 minutes. Please raise your question. Don't forget to state your name and your affiliation. And please make it short question. They will explain in details, so you don't need to explain the details. Okay, please. Anyone? Okay, the initiator for share, Dr. Pramujo. Or I will ask directly, Dr. Hendra, you should ask for photocatalyst. Student, please. Okay. You're not student, but that's okay. Okay. Please, the committee.
Okay, thank you very much. My name is Pramujo from ITB. I would address the question for Professor Nurak and also Professor Kaijian. First, about the waste processing. Maybe the sorting is the quite meticulous part of the process, I think. Can the plant handle various type of lithium-ion batteries or only single types? And for Professor Kaijian, I want to know, you use myristic acid in the dye-sensitized solar cells to attack the myristic acid, MA, yeah, for increase the attachment of the dye into the titanium oxide. Yes. It is the best compound to do that, or do you have any other things? Thank you very much.
Okay, thank you very much, Dr. Pramujo. The second one, please.
Okay, thank you very much, Professor Nurak and Dr. Kaijian Zhu for the inspirative talks. So I have questions for Professor Nurak and also Dr. Kaijian Zhu. So the first for Professor Nurak is regarding the yield of the black mass that you actually claim during the hydrometallurgy process. So I'm just wondering regarding what is the specific targeted metals that you currently aims for recovering the LIB waste. And for the Dr. Kaijian Zhu, regarding the process consisting of the organic oxidations process in order to produce the value-added products through the oxidations process, and you aim to get the glycosidic acid. So I'm just wondering how you can actually construct the anodes in this case in order to generate good selectivity towards the glycosidic acid, because there is actually a lot of derivative products that can be actually generated through the oxidation reactions.
Environmental analysis, so LCA impact, and you showed that there are two scenarios. The second scenario is, the environmental impact of two scenarios for the furnace is higher. So could you please elaborate more on the reason why it is one process is better than the other? For Professor Kajianju, so it is very interesting that you are converting so many things through photochemical reaction. So it is also interesting that you also, apart from the experimental part, you also evaluate the economic analysis. So as we know that did you calculate or include the spedition, the cost of spedition in that economic model? Thank you so much.
Okay, thank you very much. So maybe I will give the first chance to Professor Nurak. The first one is related, is it possible this plant to handle all type of LIB, like NMC, NCA, LFP, or all type? The second one is related with the yield of black mass through hydrometallurgy. Which metal do you aim specifically? And the last one related with LCA, why the reason you choose the one scenario is better than the others based on LCA itself? Please.
Thank you for the questions. After we have done some experiment in both LFP and NMC, they will give different products. We have different conditions for each raw material coming in. So the one that I show maybe only NMC, but we also have the condition to do the hydromet for the LFP as well. But of course, the LFP, after we calculate the feasible of the production is not high comparing to NMC, because the metal that used in that battery is like iron. The price is not very high, so the government may be thinking that we will select only NMC and go into the process, not the LFP. For second question, if I understand correct, you're talking about acid using.
Which metal do you want to specify the best metal during
Okay. I think the first things. Are you talking about the crushing or the incineration?
The
hydrometallurgy. Okay. We used the importance of the process come from the beginning, which is a leaching process. So the more you can extract or dissolve metal out from the back mass, will be easier to get higher products at the end. So we optimize the condition by calculate the percent of leaching percentage of that. We try different temperature, even at the large scale and medium scale, not only based on the laboratory scale. So after that, we check how much of the efficiency we can extract. So we will using that for the upscale consequently. Yes.
Targeted nickel, mangan, or?
Okay. In the beginning of the project, we focus on lithium. However, after we have done 20 liters of reactor capacity, we found that it's very, it's very good to focus on others like nickel and copper. And now we're thinking about to use electrolysis because it's using the green energy, green electricity to separate that, but that might be one possible way. Yes. So not only lithium, we also focus, later on we will focus on nickel and copper as well. And some of my colleagues, they asked me to donate them. I mean, I give them like a nickel copper for other kind of catalyst application. Yes. About the LCA, as you know that the process condition using for the incineration require a lot of natural gas and a lot of treatment. Like I mean the acid gas treatment at the end of the process. So that's why the global warming emission higher, much higher than what we use, because the crushing process require only a very small amount of electricity. So that's the question. That's the problem. And if we compare between insight into the crushing process, we found that the one that might affect to environmental, comparing to incineration process, is the toxic, human toxic, because we cannot control the sulfuric HF coming out from the process after, during the crushing, and also the some dizzy odor like a binder in that battery to coming out after during the crushing process. So that is only one. So what we are going to do is try to have a closed system as much as we can on that side. Thank you.
Okay, thank you very much, Professor Nurak. Now, please, Dr. Kaizen Zhu, to explain. The first one is related with the MA to increase the oxidation performance. What is the best compound, please?
Okay, for the first question, because we just use the myristic acid to prevent it from the twisting, therefore we only tried this one materials. I cannot say this is best, because in principle this twisting happens in the polar solvent or the polar condition. Therefore, if we can change the local environment to the apolar, therefore we can limit this twisting. Therefore, as long as the materials has a bending group, such as carbon COOH group or other groups like phosphonic group, it can bend it together with the dye on the nickel surface. Then then with an apolar chain or apolar group surround, then it can work for these applications. Therefore, there's a lot of way more like materials can be tried, of course. And also we found if we also change the ratio between the dye and this myristic acid or some other apolar compound, then it can twist it, the twisting angles. Yeah, so it is basically, cannot say it is perfect, but it's good or it works for these applications.
Okay, the second one is related with glucosidic acid and how you fabricate the anode, the anode selection itself.
The anode is just basically bismuth banded, so it's very commercial, or it's not like very mature procedures using electrodeposition. Then we transfer the bismuth iodide, bismuth iodide. No, it's hematite. It's just to use like hydrothermal to prepare the FeOH first, then we anneal it, then we get the hematite. But because for these applications, we found this selectivity to gluconic acid is very difficult because it is very easy to over-oxidize into the formic acid. And also, as you see that EG have a lot of different product. So to control selectivity is, yes, indeed it's difficult. And to control it, for example, you can try to see, for example, you use different materials, of course, then you will have different bending energy to the feedstock or the intermediate state according to the Sebastian series, then you will have optimal, I think, for some materials. But in our case, we found, also not our case, but also in the literature, we will always see they have the product, final product is formic acid. This is because I think I said that gluconic acid is very easy to be further oxidized. Therefore, in our case, we introduce another method, just to add additional catalyst, not on top of the electrode, just beside the photoanode, then which can drive the e.g. oxidation itself without the effect of the potential or the light. Yeah.
Okay, and the last question. What is the main one, please? Do you mind to
So my question is, it is very good that you did the experimental part and also the economic analysis, and you showed the levelized cost of your product. And we know that this kind of system, photocatalysis, electrolysis, has wide range of products. So in that economic analysis, did you consider the separation cost? Because sometimes it is kind of like a hurdle as well. Thank you so much.
Yes, indeed, we consider the separation cost. So we also in our calculation, especially for the gluconic acid, we considered about the separation cost. We considered about the inflation of the economic every year. And we also considered about the activity drops year by year. But of course, all these are just assumptions. We just add a factor on these values. Then, of course, it's not practical, but it has kind of indications. Yeah.
Okay, thank you very much. I forgot. Yeah, related with the levelized cost of hydrogen. It's not only the electricity, but also the separation. Okay, the next question is coming from Professor Chandra to Professor Nurak. What safeguards are in place to prevent toxic leakage and emission from used lithium battery, recycling or recovery from harming the environment?
It's a very important question, and I think right now in our plant we measure all the PM10, PM2.5, and then we sampling the emission out, and everything passed. However, the smell is not very pleasant to the worker. So we think later we will have a scrubber to and then some unit to vacuum all the fume out, go to the scrubber, and then let's see what we can mitigate those kind of pollution. Yes.
Yeah, so at least with scrubber, it's the first safeguard that normally is. Okay, thank you very much. Okay, I will open the second session. We still have more time. Anyone who wants to ask related with whether the photo catalyst? Okay, one. Mr. Janus, the second one. Any question? Yeah.
Let me introduce myself. My name is Elizabeth Kristompul. I'm from Chemical Engineering ITB. My question is for Professor Nurak. And my question is, in battery recycling, are the batteries being recycled only those that have reached their end of life? Does it also include batteries that are damaged from the cell? If the cells are damaged, what method is used before recycling? Because in such cases, discharging may not be optimal due to open circuits or internal shorts. How's about the quality black mass due to damage from the cell battery? Thank you.
Okay, very nice question. Now please, Mr. Janus, do you mind to give him the microphone, please? Here in the front row. Yes.
Thank you very much. My name is Janus from M Topindo. I asked about photocatalysis. In your presentation, photocatalysis is excitation of electron and hole plus. So to convert water OH hydroxide to radical, and then to convert again to H2O2. Yeah. Our company use H2O2 as very much and have problem about transportation. Within 1 week, I think transportation is DJ during transportation and concentration about 40% H2S. How your suggest about if we want to make in situ H2 hydrogen peroxide production, so will be give our company is more efficient and reduce risk of DJ in transportation. Thank you.
Okay, thank you very much. Okay, maybe for the first question, Professor Nurak, how if the cell itself is damaged, how would be related to the quality of the black mass, or maybe you can add the quality related with the metals itself, please.
Well, thank you. This is a big capacity plant, so we include not only the battery, which are the damage. We put everything together, just like the disposal plant, and but we didn't actually work on the effect by effect. So the waste coming in, they can be damaged or undamaged, coming together. So the product that we have is that what we are happy enough for that. So we didn't do.
There is no significant effect toward
I think so. Because after the damage, only PVDF and some release out. The metal itself still inside the case or the module.
Okay, thank you very much. So please, Dr. Zhu, what do you think with the hydrogen peroxide itself? How to make it efficient based on your photocatalytic experience?
Yeah. So for the using this method to produce hydrogen peroxide, there is not like the conventional method. It cannot produce the hydrogen peroxide as efficient as the conventional method. Therefore, using this photoelectrochemical method or electrochemical method, they all aimed for kind of application of the low concentration of hydrogen peroxide. For example, from 3 to 10% of this in the electrolyte. Then it is not needed to separate it or to transport, because it can, in this case, is good for the in situ applications. Therefore, you produce it and then you use it in the same place. Therefore, there's no risk of the transportations. And also, we do not need to separate it. There's already some demonstrations that you can generate this hydrogen peroxide and use it for some certain applications directly. Yeah.
Okay, thank you very much. Any other question before we wrap up? No, if not, I will ask the last question. First to Professor Nurak. The one that's really interesting, nowadays in Indonesia we have a lot of battery electric vehicle. Maybe drone is not that significant, but for example, the Grab online, they use normally the electric motor with a lot of battery waste. And normally they still use LFP instead of NMC. Like you mentioned previously, LFP is relatively cheap if we want to extract the metals itself. So is it possible to combine both? Because sometimes the collector cannot distinguish which one is LFP, which one is NMC. LFP is lithium pyrophosphate that you mentioned previously, while maybe NMC only famous car that normally used here in Indonesia. But LFP, a lot of cars, motorcycle, they use LFP base. What do you think about that? Please.
Thank you. Well, we have done the work on LFP, and the conditions still work, but the profit margin not very good.
Okay.
Yes. NMC, even from the motorbike. Yes.
Okay, okay. So in Thailand, you have a lot of NMC, even in motorbike.
I think the company that I asked the waste from is big bike, like a EV big bike.
Okay, EV big
So
bike.
that's
For
why
touring, maybe.
Yes,
Okay.
for the traveling.
Okay, okay.
And not from rider or
City
Grab.
days.
Right.
Okay.
But the LFP, lithium compound, the production of lithium is in the border of the profit because of the wastewater treatment. Yes.
Okay.
Not about the efficiency or what we can get from the LFP.
Okay,
Yes.
okay, perfect. Thank you very much. And last question to Dr. Zhu. It's when you prepare the dye with a lot of modification, is it possible to be used in, like in Indonesia, we have a lot of, the structure itself is archipelago. We have a lot of island with a lot of water itself, more than 70%. So the issue will be related with precipitation. Maybe within a year, the sunny days without any cloud less than a month. What do you think the prospect in the future for the country like us?
Yeah, for this dye sensitive electrode, if you want to use it for the catalytic reaction, it's difficult because as said, nowadays performance is very, very low, but it can be used as a solar cell. Because now, especially in some country, for example, Switzerland or Denmark, they already have large-scale applications. For example, the windows, they covered with dye-sensitive solar cell, then it can generate the electricity from that. Therefore, the applications for the solar cell is already achieved in the real world. But for the catalyst, for example, water splitting or this kind of reaction, it is far away from the application yet because the performance is too low nowadays. Yeah.
Okay, thank you very much. So to wrap up, you already hear the future energy is not only based on fossil fuels anymore. A lot of opportunities, a lot of alternative. One of them is photocatalyst with dye-sensitized system. It can be used directly as industrial application as well. The second one from Professor Nurak mentioned, we don't need to worry about the disrupting technology of the battery, as long as we know how to handle it. So recycle might be one of the solution, but maybe at a certain point the issue would be related with the environment, particularly with water treatment, right? So let's give them the big applause for our distinguished speaker. Thank you very much. So let me return back to the Master of Ceremony. Please have a seat.
We would like to extend our sincere appreciation to Dr. Hari Devianto and to all our distinguished speakers, Professor Nurak and Dr. Zhu, for their valuable contributions and insightful knowledge in the session.
At this moment, we will proceed with the awarding of certificates and tokens of appreciation to our speakers and moderators. We are honored to invite Dr. Tirto Prakoso as the Dean of Industrial Technology Faculty at Institut Teknologi Bandung to kindly present the certificate.
Once again, thank you for the session. Now you may go back to your seat. Ladies and gentlemen, now we will have a short coffee break for 15 minutes.
To all of the participants, please come back at 2:55 p.m. We have two different coffee break stands located at the east and west wing of this building. So remember, please come back at 2:55 p.m. Thank you and have a pleasant coffee break.
International Seminar on Chemical, Food and Chemurgy Engineering Suhadi Reksowardoyo, or STKSR, is an annual seminar organized by Department of Chemical Engineering, Institut Teknologi Bandung. In this conference, scholars and practitioners around the world share ideas and scientific achievements for development of various process technology. What was the history behind this annual seminar? We are going to find out.
Pak Suhardi itu salah satu dari 2 orang pertama yang dapat predikat cum laude lulusnya. Jasa beliau terbesar itu, pertama beliau itu yang memimpin nasionalisasi industri kimia. Beliau sebetulnya pencetus Tridharma perguruan tinggi.
Dengan adanya Tridharma perguruan tinggi, ada pendidikan, penelitian, dan pengabdian kepada masyarakat. Sehingga ITB, salah satu perguruan tinggi yang memulai adanya LAPI. LAPI itu adalah lembaga afiliasi dan penelitian industri.
Pak Suhardi itu juga sebetulnya yang membangunkan kembali tradisi riset atau kebiasaan riset di perguruan tinggi. Tahun 1991 ada peringatan 50 tahun pendidikan tinggi teknik kimia di Indonesia. Sebenarnya itu seminar tahun 92. Terus kita namakan seminar teknik kimia Suhadi Reksowardoyo.
Tapi untuk informasi saja bahwa seminar teknik kimia ini belum diberi nama Suhadi Reksowardoyo. Itu sudah diadakan setiap tahun.
Ya sebetulnya kan dulu itu merupakan ajang pertukaran dari dosen-dosen dan peneliti ya. Jadi orang bisa menghadiri lalu bertukar pikiran dengan sesama peneliti, sesama dosen.
Kemudian kenapa nggak diberi nama itu supaya unik? Hanya seminar teknik kimia, jurusan teknik kimia, gitu kan? Banyak jurusan teknik kimia di Indonesia. Tapi begitu Suhadi Reksowardoyo hanya di untuk menghormati jasa-jasa. Saya melihat beliau sangat rapi.
Tenang, memperhatikan yang muda-muda.
Dulu profesor di ITB di teknik kimia, sangat seperti itu. Suhadi ini salah satu profesor, sehingga namanya itu profesor pertama orang Indonesia.
Ya, Pak Suhadi itu bukan hanya pinter ya, tapi dia bisa membangun budaya institusi budaya riset. Nah, sekarang ini sebetulnya kontribusi Pak Suhadi besar.
Beliau itu banyak sekali kegiatan yang berhubungan dengan penugasan dari pemerintah. Salah satunya adalah pernah menjadi menteri, yaitu sama saya tahun 66.
Jadi waktu Presiden Soekarno bikin tahun 66 reshuffle kabinet, 100 menteri kabinet, nah Pak Suhadi itu menteri riset.
Ya dengan semakin banyaknya prodi-prodi atau jurusan teknik kimia di Indonesia, memang sebenarnya juga sangat berkembang. Dan yang perlu dipahami juga teknik kimia sekarang sangat disorot. Kalau buka buku karangan seorang ekonom namanya Rosenberg, itu mengatakan bahwa teknik kimia is a general purpose technology. Itu apa? Adalah teknik engineering yang bisa mengubah ekonomi suatu negara. Jadi ini kan harus ditunjukkan betul bahwa memang kita bisa melakukan semuanya. Seiring dengan ya sekarang bergeser dari fasilitas teknologis, kita yang bisa melakukan. Sehingga dalam beberapa hal kita bisa
International Seminar on Chemical, Food and Chemical Engineering Suhadi Reksawardoyo or STKSR is an annual seminar organized by Department of Chemical Engineering Institute Teknologi Bandung. In this conference, scholars and practitioners around the world share ideas and scientific achievements for development of various process technology. What was the history behind this annual seminar? We are going to find out.
Pak Suhadi itu salah satu dari 2 orang pertama yang dapat predikat cum laude di USU. Jasa beliau terbesar itu pertama beliau itu yang memimpin nasionalisasi industri kimia. Beliau sebetulnya pencetus Tridharma perguruan tinggi.
Dengan adanya Tridharma perguruan tinggi, ada pendidikan, penelitian, dan pengabdian kepada masyarakat. Sehingga ITB salah satu perguruan tinggi yang memulai adanya LAPI. LAPI itu adalah lembaga afiliasi dan penelitian industri.
Pak Suhadi itu juga sebetulnya yang membangunkan kembali tradisi riset atau kebiasaan riset di perguruan tinggi. Tahun 91 itu ada peringatan 50 tahun pendidikan tinggi teknik kimia di Indonesia. Sebenarnya itu seminar tahun 92. Terus kita namakan seminar teknik kimia Suhadi Reksawardoyo.
Tapi untuk informasi saja bahwa seminar teknik kimia ini belum diberi nama Suhadi Reksawardoyo, itu sudah diadakan setiap tahun.
Ya sebetulnya kan dulu itu merupakan ajang pertukaran dari dosen-dosen dan peneliti ya. Jadi orang bisa menghadiri lalu bertukar pikiran dengan sesama peneliti, sesama dosen.
Kemudian kenapa nggak diberi nama jadi supaya unik, hanya seminar teknik kimia, jurusan teknik kimia gitu kan, banyak jurusan teknik kimia di Indonesia. Tapi begitu Suhadi Reksawardoyo hanya di untuk menghormati jasa-jasa. Saya melihat beliau sangat rapi.
Tenang, memperhatikan yang muda-muda.
Dulu profesor di ITB di teknik kimia, sangat sepuh. Nah, Suhadi ini salah satu profesor. Nah, sehingga memang itu profesor pertama orang Indonesia.
Ya, Pak Suhadi itu bukan hanya pinter ya, tapi dia bisa membangun budaya institusi dulu, budaya riset. Nah, sekarang ini sebetulnya kontribusi Pak Suhadi besar.
Beliau itu banyak sekali kegiatan yang berhubungan dengan penugasan dari pemerintah. Salah satunya adalah pernah menjadi menteri, yaitu selesai tahun 66.
Jadi waktu Presiden Soekarno bikin tahun 66, reshuffle kabinet, 100 menteri kabinet, nah Pak Suhadi itu menteri riset.
Ya dengan semakin banyaknya prodi-prodi yang jurusan teknik kimia di Indonesia memang sebenarnya tidak. Dan yang perlu dipahami juga teknik kimia sekarang sangat disorot. Kalau buka-buka buku karangan seorang ekonom namanya Rosenberg, itu mengatakan bahwa teknik kimia is a general purpose technology. Itu apa? Adalah teknik atau engineering yang bisa mengubah ekonomi suatu negara. Jadi ini kan harus ditunjukkan betul kalau memang kita bisa melakukan semuanya. Seiring dengan ya sekarang bergeser dari fasilitas ekonomi ke ekonomi, kita yang bisa berkonsumsi. Sehingga dalam beberapa hal kita bisa berperan besar dalam mengubah perekonomian di Indonesia.
International Seminar on Chemical, Food, and Chemical Engineering Suhadi Reksowardoyo or
850 Masehi merupakan masa di mana Indonesia membuktikan kecerdasannya melalui karya agung nenek moyang dalam wujud Candi Prambanan. Menjadi salah satu situs warisan dunia berdasarkan UNESCO, candi ini merupakan lambang kerja keras, kecerdasan, dan anugerah yang Maha Esa atas diri nenek moyang yang patut dibanggakan oleh seluruh generasi masa kini dan masa yang akan datang. Berbekal tekad untuk mewarisi semangat berkarya nenek moyang, PT Zeus Kimia Tama Indonesia dilahirkan. Berawal di tahun 1998 di sebuah rumah kecil di Bekasi, mimpi Zekindo untuk membangun industri kimia di Indonesia dimulai. Pada tahun 2005, blending plant pertama mulai beroperasi di kawasan industri Greenland Delta Mas Cikarang Pusat. 1 tahun kemudian, didirikanlah PT Acme Indonesia, anak perusahaan pertama PT Zeus Kimia Tama Indonesia. Dalam mengikuti perkembangan bisnis, pada tahun 2014, PT Zeus Kimia Tama Indonesia memulai aktivitas produksi pada pabrik 1 di kawasan industri Lipo Cikarang. Pada tahun 2016, kantor pemasaran negeri PT Zeus Kimia Tama Indonesia mulai beroperasi. Pada tahun 2020, didirikanlah PT Power Indo Kimia Mineral. Pada tahun 2022, pabrik 2 mulai beroperasi di kawasan industri Kota Bukit Indah, Purwakarta. Pada tahun 2023, PT Zeus Kimia Tama Indonesia melakukan proses pemindahan pabrik 1 ke main plant Jababeka. Berawal dari pabrik kecil di tahun 1998 dan berbekal pengalaman lebih dari 25 tahun, PT Zeus Kimia Tama Indonesia sebagai perusahaan manufaktur bahan kimia khusus secara konsisten hadir untuk melayani konsumen dengan pelayanan terbaik. Hingga kini, kami terus mengembangkan produk berkualitas tinggi yang mampu berkompetisi di kancah internasional demi mendukung pelanggan kami di Indonesia, kawasan ASEAN, dan berbagai negara lainnya dalam bidang pengolahan air dan limbah, minyak dan gas, gula dan bioetanol, enzim, tekstil, otomotif, cat dan pelapisan, serta aplikasi pertambangan dan pengolahan mineral. Tidak hanya mengedepankan produk dengan kualitas tinggi, pembangunan berkelanjutan juga menjadi aspek penting bagi kami. Melahirkan generasi muda yang kompeten dan berdaya saing menjadi prioritas kami. Untuk itu, kami turut melibatkan generasi muda Indonesia dalam kolaborasi penelitian produk serta program beasiswa bagi pelajar berprestasi. Kami berkontribusi untuk mewujudkan green industry melalui program pengolahan limbah berbasis biologis serta peningkatan kualitas udara berbasis green algae. Kami berkomitmen untuk menciptakan lingkungan kerja yang menjunjung tinggi keselamatan bagi seluruh karyawan berbasis manajemen mutu yang diterapkan dalam ISO 4501 agar dapat tercipta lingkungan kerja yang sehat dan seimbang demi mencapai kesejahteraan lingkungan dan masyarakat. Dengan pengalaman lebih dari 25 tahun, dibantu oleh 150 tenaga ahli dan bekerja sama dengan perusahaan-perusahaan terbaik, kami berkomitmen untuk menghasilkan produk lokal berupa bahan kimia khusus yang berkualitas tinggi, kompetitif, dan berstandar internasional untuk mendukung pelanggan kami dalam berbagai industri.
cerita akselerasi kita yang selalu aja ada tantangan pas kita lagi melesat.
Berat banget ya.
Mau nyerah aja, enggak kan?
No lah, big no.
Bagus, ini waktunya akselerasi. Makin banyak tantangan, makin banyak jalan. Ya nggak sih? Asal... Nah gitu. Kalau mau berakselerasi itu harus rame-rame.
Rame ini.
Yes, mantap.
Menyala bangku.
Yeah. Gak cuma sekedar wujudin mimpi, tapi ciptain inovasi. Semangat akselerasi ngedorong kita untuk terus berkolaborasi. Biar ngasih impact positif buat bangsa Indonesia. Ayo, wujudin swasembada energi dengan terus berakselerasi tanpa henti. Pertamina, energizing the acceleration.
Attentions, everyone. So please check your belonging, and if you feel like you lost a debit card, please contact us. Please contact the committee for reclaiming this card. Thank you.
Berdasarkan UNESCO, candi ini merupakan lambang kerja keras, kecerdasan, dan anugerah yang Maha Esa atas diri nenek moyang yang patut dibanggakan oleh seluruh generasi masa kini dan masa yang akan datang. Berbekal tekad untuk mewarisi semangat berkarya nenek moyang, PT Zeus Kimia Tama Indonesia dilahirkan. Berawal di tahun 1998 di sebuah rumah kecil di Bekasi, mimpi Zekindo untuk membangun industri kimia di Indonesia dimulai. Pada tahun 2005, Blanding Plant pertama mulai beroperasi di kawasan industri Greenland Delta Mas Cikarang Pusat. 1 tahun kemudian, didirikanlah PT Acme Indonesia, anak perusahaan pertama PT Zeus Kimia Tama Indonesia. Dalam mengikuti perkembangan bisnis, pada tahun 2014, PT Zeus Kimia Tama Indonesia memulai aktivitas produksi pada pabrik 1 di kawasan industri Lipo Cikarang. Pada tahun 2016, kantor pemasaran grup PT Zeus Kimia Tama Indonesia mulai beroperasi. Pada tahun 2020, didirikanlah PT Power Indo Kimia Mineral. Pada tahun 2022, pabrik 2 mulai beroperasi di kawasan industri Kota Bukit Indah, Purwakarta. Pada tahun 2023, PT Zeus Kimia Tama Indonesia melakukan proses pemindahan pabrik 1 ke milik plant Jababeka. Berawal dari pabrik kecil di tahun 1998 dan berbekal pengalaman lebih dari 25 tahun, PT Zeus Kimia Tama Indonesia sebagai perusahaan manufaktur bahan kimia khusus secara konsisten hadir untuk melayani konsumen dengan pelayanan terbaik. Hingga kini, kami terus mengembangkan produk berkualitas tinggi yang mampu berkompetisi di kancah internasional dan mendukung pelanggan kami di Indonesia, kawasan ASEAN, dan berbagai negara lainnya dalam bidang pengolahan air dan limbah, minyak dan gas, gula dan bioetanol, enzim, tekstil, otomotif, cat dan pelapisan, serta aplikasi pertambangan dan pengolahan mineral. Tidak hanya mengedepankan produk dengan kualitas tinggi, pembangunan berkelanjutan juga menjadi aspek penting bagi kami. Melahirkan generasi muda yang kompeten dan berdaya saing menjadi prioritas kami. Untuk itu, kami turut melibatkan generasi muda Indonesia dalam kolaborasi penelitian produk serta program beasiswa bagi pelajar berprestasi. Kami berkontribusi untuk mewujudkan green industry melalui program pengolahan limbah berbasis biologis serta peningkatan kualitas udara berbasis green algae. Kami berkomitmen untuk menciptakan lingkungan kerja yang menjunjung tinggi keselamatan bagi seluruh karyawan berbasis manajemen mutu yang diterapkan dalam ISO 4501 agar dapat tercipta lingkungan kerja yang sehat dan seimbang demi mencapai kesejahteraan lingkungan dan masyarakat. Dengan pengalaman lebih dari 25 tahun, dibantu oleh 150 tenaga ahli dan bekerja sama dengan perusahaan-perusahaan terbaik, kami berkomitmen untuk menghasilkan produk lokal berupa bahan kimia khusus yang berkualitas tinggi, kompetitif, dan berstandar internasional untuk mendukung pelanggan kami dalam berbagai industri.
cerita akselerasi kita yang selalu aja ada tantangan pas kita lagi melesat.
Berat banget ya.
Mau nyerah aja, enggak kan?
No lah, big no.
Bagus, ini waktunya akselerasi. Makin banyak tantangan, makin banyak jalan. Ya nggak sih? Asal. Nah gitu. Kalau mau berakselerasi itu harus rame-rame.
Rame ini.
Yes, mantap.
Menyala bangku.
Yeah. Gak cuma sekedar wujudin mimpi, tapi ciptain inovasi. Semangat akselerasi ngedorong kita untuk terus berkolaborasi, biar ngasih impact positif buat bangsa Indonesia. Ayo, wujudin swasembada energi dengan terus berakselerasi tanpa henti. Pertamina, energizing the acceleration.
International Seminar on Chemical, Food, and Chemistry Engineering Suhadi Reksawardoyo, or STKSR, is an annual seminar organized by Department of Chemical Engineering, Institut Teknologi Bandung. In this conference, scholars and practitioners around the world share ideas and scientific achievements for development of various process technology. What was the history behind this annual seminar? We are going to find out.
Welcome back, everyone. We hope you enjoyed the coffee break and had a chance to recharge and catch up with friends and colleagues.
Indeed, enjoying coffee together while exchanging stories or maybe ideas and running relationships with others is always a delightful way to reconnect and re-energize. Let us now continue.
We're now moving into the third plenary session, which will focus on an important theme, renewable energy for sustainable development. This session promises to provide deeper insights and valuable perspectives.
We are honored to have Dr. Anton serves as the moderator of these sessions. May we kindly invite Dr. Anton to join us and lead the third plenary sessions.
Okay, thank you very much. Good afternoon, all distinguished guests, ladies and gentlemen, and also all participants of International Seminar or Chemical Process Engineering Suhadi Reksawardoyo 2025. Yeah. So let's start this final session, the third session of our plenary lecture. And this session, I think we have very prominent speaker, yeah, from Pertamina, that I would like to invite him to come up to the stage. And let's give us applause to Mr. Dr. Oki Muraza. Please, Pak. Yeah. Okay. Dr. Oki Murasa is actually currently become the Deputy President Director of PT Pertamina Group. Yeah. And I think the complete curriculum vitae is already here that we can see from the screen. Okay, and then let's start the presentation for Dr. Oki. Dr. Oki, 30 minutes for your presentation. Okay, and then next we will have a discussion. Yes, please.